Hi, my name is Andy Slippy. I'm a senior engineer at Advanced Cooling Technologies, and today we're going to be talking about how we select working fluids for pump two-phase systems. So the history of pump two-phase, and we use a lot of refrigerants and things, so typically those have been developed for vapor compression systems, and originally they would have been things that were very flammable. Propanes and things like that were used. We got away from flammability, and new lines of refrigerants were invented. It turned out those, after a few decades of use, found out that those were eating the ozone layer. So those were eliminated, are being eliminated, and a new set was created, and now a lot of those cause global warming. So there's a new version of refrigerants being introduced that the chemists are coming up with. And so when we find these new fluids, how do we decide whether they're a good fit for pump two-phase? So we look mostly at the properties of the fluids. Fluids have a phase diagram. You can have a pressure and temperature diagram here, and it typically has something that sort of does this, where at very cold temperatures or very high pressures you have solid material. Over here we have gases, and in between are liquids. And pump two-phase, we are dealing with moving across this line between liquid and gas. This point right here, I'm going to move it up a little higher, is the critical point. Beyond this, in this region, is what's called supercritical fluids. Strange things happen up there. We don't have normal phase change, so they don't work very appropriately for pump two-phase. So one of the first considerations is what temperature is your application working at? Is your fluid in that temperature? Are we somewhere in this range where we can actually be moving between liquid and gas? And then where are you in that range? So there's a couple different things. We want to be, typically we want to be operating closer to the critical temperature for a couple reasons, but obviously, like I said, not beyond the critical point. So a couple of those reasons are, one is heat transfer coefficients. Heat transfer coefficients are typically better when the operating pressure is closer to the critical pressure. And the second reason is due to a controls application. So this curve tends to get steeper as you move out, and we often, pump two-phase applications are looking for very precise control of temperature. And so in order to do that, it is easier to measure and control pressure. So if you're out here on this part of the curve, you could have a fairly large change in pressure that would result in a fairly small change in temperature. And so at that point, you can adjust that pressure within this band and have very small temperature changes. If you're down here on the curve, very small pressure fluctuations will result in much larger temperature changes due to the slope of that curve. So we want to be up on this portion of the curve, and all that is going to depend on what temperature your application is actually at. The other consideration, and this is kind of the reverse, is that you can also have a diagram of pressure and enthalpy. And on this plot, there's something called the liquid vapor dome here, where on this side of this plot is liquids, over here is gases, in here is the two-phase region. On this plot, a line of constant temperature looks something like this, and you would have multiple lines of different temperatures. So what this is showing is that as you're adding energy to a fluid, typically your temperature increases, except when you're in the two-phase region, when you're adding the energy, the temperature stays constant. And then again, when you get out into the gas, as you're adding energy, the temperature is continuing to increase. This two-phase region where this is constant is what we're trying to take advantage of in pump two-phase. And so the length of the line in this region corresponds to how much flow we have to pump in order to take however much heat we're trying to dissipate in that particular case. So you can see that on this plot, which I didn't label it, but up here is this critical point. So this is the exact same point as that. As you get very close to that critical point, these domes are differently shaped for every fluid, but it's fairly consistent that the size, the amount of energy that you have at a constant temperature becomes less and less as you get up there. So while we want to be close to the critical point for controllability and heat transfer, the closer you are, the more flow rate that you'll have to supply, because you'll have less latent heat. The distance here is called the latent heat of vaporization. So those are the things that we have to balance, and then on top of that, dealing with all the other implications of the fluids, flammability, toxicity, and all of that. So when you come to ACT with a pump two-phase application, this is the type of analysis that we will start with to try to find out what fluid to work with based on primarily what temperature you're trying to work at. So if you are interested in more details, there should be links to our website somewhere, and there you can go there for more information.